I think it's a good choice. Take the top. What's that?
What's the difference between?
Nothing. They do say the exact same thing. Are you saying how it will result?
Yeah.
Because when you take the derivative of ln x and be 1 over x. If you take the derivative of this, that's just a product. This is that power rule.
Okay.
You can pretend this is x to the negative first. And so we have 1 over x, and you're going to get something over x squared. They're going to cancel, and you have a very simple expression here. Over here, you got 1 over ln x. So I got to do like a quotient rule on it, and play a little game with it and stuff. So it's just a little messier derivative. They should both work fine, but I'm just saying in terms of simplicity, this one's probably the simpler path to go. You won't know that in advance, but if you do more problems, you'll develop a little bit of intuition about it.
This would be a infinity over infinity case, because when ln of
That's
0.
right. You have changed to an indeterminate quotient of infinity over infinity. All these changes, you don't really need to check them each time. They should always work out, okay? As long as you truly start with an indeterminate power, when you make these changes to the logarithm and change to a quotient, it should turn out to be an indeterminate quotient. It should be indeterminate, okay? So you don't have to check along the way. It's a good idea, but I don't know if that's necessary. All right, so now that I have an indeterminate quotient, I want to take the limit of that. Remember, you were taking the limit of an altered function. You're not taking the limit of the original function right now. You're taking the limit of the previous, taking the limit of the new function with ln applied. So limit of ln x over 1 over 2x as x goes towards 0 from the right. So you should be able to apply L'Hopital's rule now. It's an indeterminate quotient, and you will get limit as x goes to 0 from the right of 1 over x for the logarithm divided by, if you treat x as x to the negative first, it will become negative 1 over 2x squared. Right? The derivative of 1/2 x, you don't lose a quotient wrong, that's just silly. So treat it as x to the negative first, you bring the negative down, and change that to a negative 2, right? That'd be the derivative. But x to the negative 2 is the same as an x squared on the bottom. So I'm writing like that. Now, just take the reciprocal and multiply through. One over x times negative 2x squared over 1. X goes to 0 from the right. And x cancels from each factor. I guess you can say that one's canceled, so whatever. So you have negative 2x as x goes to 0 from the right. So what's the answer?
0.
The answer to this part of the problem is 0. That is not the answer to the original limit. Why? Because we took natural log. We changed the function from x to the 2x to the natural log of x to the 2x. We ran the limit on this expression, the red expression. So we need to now change it to the answer to the green expression. So how do you undo a logarithm?
E?
Exactly. So our answer is e to that value. One. You're right. Right. Answer is 1. So don't forget to change back to the end. Always rate whatever value you get. Make sure you raise it as an exponent to e at the end of the problem, and that's your final answer. As an exponent, right?
Where do you put the 0?
Right there. Here, let me help you print it. Put 0 right there.
That helped a lot.
Okay.
I have a question. What exactly does E stand for?
It an irrational number, like 2.7, around 2.7, but it's an irrational number.
I know it's 2.7, but why E?
Are we using e in the problem, or why is e, like in general, why are we using e?
It stands for exponent.
It doesn't. It stands for Euler. It's Euler's number. So, because we first applied a natural log to this expression, so we can bring the 2x down, right? Using properties of logs. Okay. So we used the log to begin with. But the inverse of a log is an exponential. So for natural log, it's that particular exponential, base e. So we're just trying to undo the natural log thing we did at the beginning. So we have to use e to some power. If you'd applied log base 2 at the beginning, which you could do, it's probably not the best idea because it makes it a little more cumbersome, you would write 2 to that number at the end. Right? Whatever base you use here, you're going to use that base at the end to undo what you did. You change the problem, basically. You change the problem, you got to change your maps. Let's try a different one. 43. limit as x goes to 0 again, we have a different indeterminate power this time. Hopefully you can figure it out. 1 plus x to the cot x. That's a strange function. So which indeterminate power is it?
It's 1 to the infinity.
1 to the infinity, right? Clearly the base is heading towards 1. And we remember from 5 seconds ago, or 5 minutes ago, the cot of 0 was infinity. That oral problem we did it took half an hour. So this is the 1 to infinity case. Alright, so we'll apply a natural log to the function inside first, so that we can take out the cot x to the outside. Log 1 plus x. We would like to change this to a quotient, so the natural thing to do is just make it a tan underneath, right? Would be the most, I don't know if it's obvious, I'm just saying the most obvious thing. Agreed? Okay? And I told you before that it should automatically change into indeterminate quotient, and it has. As x goes to 0 on this expression, it's heading towards natural log of 1, which is 0, and tan of 0 is 0, it's heading towards 0, 0 case, right? 0 to 0 now. So we can apply the L'Hopital's rule. So the limit of the changed expression, ln 1 plus x over, I have a game called secant squared, tan x, as x goes to 0 from the right, should be the same through L'Hopital's rule as the limit of the derivatives. So the derivative of ln 1 plus x is simply 1 over 1 plus x, and the derivative of the tan is the secant squared. So now just see what's happening as x goes to 0. The top's heading towards 1, and the bottom's heading towards 1. So the answer is 1 for this part of the problem. There we go. We gotta change it back though. We applied natural logs, now apply e. The final answer to this is really e to the first, which is e. The answer is e. Any questions about indeterminate powers?
Quick question. When you brought down the cotangent of x to the front, but what happened to the cotangent of x that was originally there?
I made it tan.
You made it 10?
From here to here, you're saying?
Well, where you say 1 plus x to the cotangent of x, and then you know how you brought it down?
Yeah, I just brought the function down.
Yeah,
I need to change this. I need to apply a natural log to it, so that I can remove this to the front and make it a product.
Why do you introduce natural log?
Why do I introduce natural log?
Yeah.
Just so I can apply the rules of logarithms and take this power down as a coefficient. That's the only reason. So no questions about L'Hopital's rule? Did quite a few of them, and a couple nasty ones.
Every time I type in what you just did, the problem before this, the derivative of ln of x over 1 over 2x in Wolfram.